Welcome back, my dear students and whoever is watching this program. So, we were in the process of discussing concepts of radioactivity for grade 12, and we just mentioned about the contribution by Becquerel, and I have shown a video. It indicates the the process of radioactivity and the phenomenon and a few aspects related to that. Whereas, in by the Rutherford's experiment, only he found out that there are three types of radiations coming out from the nucleus, namely alpha, beta, gamma. So, first let us see what was that experiment, how it explained or how it proved that there are three types of radiations coming out from a nucleus. That is, he has taken an electric field, then a magnet. Even in magnetic field, he found that the radiations coming from the nucleus, they are separated into three. Okay, so I will show you how the experiment was by Rutherford, which indicated the three types of radiations coming from the nucleus. You just watch this as well. Okay, watch it.
Of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into three components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-rays.
Okay, that's it. That's indicating the experiment conducted by Rutherford on separating the three radiations, or in fact two particles and a radiation. Okay, so of which alpha particle, beta particle and gamma rays, when we say, we have seen from the video clearly that alpha is nothing but a helium nucleus. That means when alpha is going out, a helium nucleus is going out. So, what is the outcome of that? When helium nucleus goes out, it means, say for example, you take a nucleus whose which has got mass number. Say nucleus has mass number, let us say 70, and atomic number, mass number is there are 70 neutrons and let us say 50 protons. Just assume there is a nucleus like this. If it is giving out a an alpha particle, what will be the outcome? What will be the new nucleus, or what will the new nucleus consist of? The new nucleus will consist of, see, alpha is going out. Alpha means it is a helium nucleus. That means two protons and two neutrons are going out. When two protons and two neutrons are going out, it further means it will have only 48 protons and 68 neutrons. So, the new atomic number for this would become what? 48 instead of 50. So, new atomic number before it was atomic number before it was 50. Now, the new atomic number is 48. So, atomic number decreases by 2. That is one change. See, mass number here, it was like 70 plus 50 mass number, which is number of nucleons, or nucleon number we call it. So, it was 120. 120 was the mass number. Okay, but here the mass number becomes how much? It becomes 116 when you add these two. Correct? Yes, 116. So, what we understand from this the mass number decreases by 4, whereas atomic number decreases by 2. This is something which you have to conclude first. So, let me tell you in short, in brief I will tell you, when an alpha particle is emitted from a nucleus, its atomic number decreases by 2, whereas mass number decreases by 4. Be very clear on that. Okay. Second thing, when a beta particle goes out, that is another area we have to be careful about. When a beta particle goes out, actually what is a beta particle? Beta particle is nothing but a an electron. Beta particle is an electron, right. So, when beta particle goes out, an electron is going out from where? From the nucleus. But from nucleus electrons cannot be emitted, no, because there are no electrons inside the nucleus. So, what is happening at the beginning of a nuclear reaction of or emitting of beta particles? Just it was also shown in the video I showed you, that is initially a neutron will decay to a proton and an electron. So, inside the nucleus, when it becomes unstable during the beta particle emission, a neutron decays to a proton and an electron. So, what happens to the electron? Electron is what is nothing but the beta particle. So, the electron is emitted from the nucleus as beta particle, whereas proton stays inside the nucleus. That is why we say, so proton stays inside the nucleus. So, atomic number will increase by 1, because proton number is atomic number or proton number, right. Proton number increases by 1. How about atomic number, mass number or nucleon number? Nucleon number will remain the same, because one neutron is decreased, or there is a decreasing of decreasing by 1, whereas increasing of proton by 1. So, one proton increased, one neutron decreased. So, the sum will again be the same. So, what is the outcome? During the beta particle emission, atomic number increases by 1, whereas mass number remains the same. This is what is happening in beta decay, right. But there is one extra aspect to understand this. During beta decay, there is one more particle emitted, which is later on it was we were not able to detect about those particles because of the its weak interaction with the matter. That particle is what is called neutrinos. You might have heard of neutrinos. Okay? Neutrino is one of the elementary particles. So, during beta particle emission, even neutrino also is coming out. Neutrino, we were not able to detect about neutrinos for a long time because of its weak interaction, because neutrino is considered to be a chargeless and almost massless particle. And what's the significance of, or what's the importance of emission of neutrino? Because the neutrino shares energy with beta particle emitted. That's the case. I hope it is clear. So, during beta decay, a neutron initially decays into a proton, an electron and a neutrino, right. It is in fact neutrino also two types, neutrino and anti-neutrino. So, what is coming over here in beta decay, negative decay is, it is an anti-neutrino. So, more precisely we can say a neutron when decays, it becomes a proton, an electron and an anti-neutrino, of which the anti-neutrino and electron will come out from the nucleus. Electron will come out as beta particle and proton stays inside the nucleus. So, ultimately atomic number or the proton number increases by 1, whereas mass number remains the same as far as beta decay is concerned. How about gamma ray decay? Gamma is not a particle, it is just an electromagnetic radiation, EM wave. So, what happens is there is no change, change in either atomic number or mass number. So, mass number and atomic number do not change in the case of gamma ray emission. Okay, that is what is the situation with gamma decay. So, I mentioned about alpha decay, beta decay and gamma decay. All right, now some terms we have in radioactivity to learn. Okay, first one is what you call as half-life. Okay, what do you mean by half-life? Half-life is, in fact, it will represent it with T half. Okay, half-life indicates, like a nucleus is getting transformed into different nuclei due to the emission of these radiations. Okay, radioactivity means it is getting transferred to newer and newer nuclei. So, this transformation takes place in how much time it will, by how much time it will become half the initial amount, that is half-life. Say an example I will tell you. The carbon 14, you must be familiar with that, carbon 14. Carbon 14's half-life is, it is one of the longest half-lives, 5730 years is the half-life of carbon 14. So, that means now whatever is the carbon 14 content somewhere, same suppose it is 10 grams. Okay. After 5730 years, it will become 5 grams, half it would become, that much time. But there are nuclei which possess half lives even in microseconds also. Okay, so an example to understand the concept. Suppose now a nucleus is, let us say, 10 grams mass. Okay, and let me say its half life is just 5 minutes. 5 minutes is the half life. So, it means what, after 5 minutes this will become how much? 10 gram, it will become 5 grams. Then in one more 5 minutes if you go, it will become 2.5 grams. In another 5 minutes it will become 1.25 grams, half like that. So, how much time it will take for it to become 10 grams to 1.25 grams? How much time? 5 plus 5 plus 5, 15 minutes it takes. So, in 15 minutes, the radioactive substance of half life 5 minutes will become how many, what fraction it will become? It becomes 1/8. This is half, this is 1/4, this is 1/8. So, we can generalize that way. If there are, let us say, n half lives, if there are n half lives, we will say the fraction left. See, let me write n by n0 as the fraction left. N represents the number of radioactive atoms present at present now, okay, and n0 is the original number of atoms. So, it took a time t to become this much. Okay. So, suppose in the total time there were n half lives, then we can see the fraction left would be 1/2 raised to n. We have seen 1/2 into 1/2 into 1/2 like that, n times. So, here n, what does n represents? What does n represent? N represents the number of half lives. I hope it is clear. So, n is the number of half lives. So, n by n0 represents the fraction left. Clear. So, now an example I will tell you. I will give an example. Suppose it is found that a radioactive substance becomes 1/32 of its initial amount in say 30 days. In 30 days, it is found that in 30 days we found that a radioactive substance becomes 1/32 or 1/32 of the initial amount. There is a fraction left. So, the question is, what is the half life, right? What is the half life of a substance, radioactive substance which becomes 1/32 of the initial amount in 30 days, right? So, 30 days. So, total time taken is 30 days. So, we just need to find how much or how many half lives are required for it to become 1/32. So, what you will write is make use of this one. This n by n0, n is the n is what is left and this is original. So, what you can say, this is nothing but a fraction left. So, we can replace this part with what? 1/32 is equal to 1/2 raised to n. So, from this we understand that n is equal to 5. That means there are 5 half lives in total, 5 half lives in 30 days. 30 days, 5 half lives. So, what will be the value of one half life? The half life is equal to, total time is 30 days now. So, there are 5 half lives. So, the answer is 6 days. Is that clear? So, what was the question? A radioactive substance becomes 1/32 of its initial amount in 30 days. So, what is its half life? That was the question. So, the fraction left is this much and we see that 5 half lives are present or 5 half lives are required for it to become this much fraction. But sometimes the question would be like it decays by an amount. So, for example, the same question if it is asked like suppose a radioactive substance decays by 31/32 of its initial amount, decays by 31/32. Okay. When you say decays by, that means that much is gone. 31/32, it decays by this much. So, that much is gone. So, what is left? So, even if this is given like this, what is left will be just remaining, that is 1/32 only is left. So, that is again this is the answer. Clear. Now, let us see what about the what you say the penetrating powers of alpha, beta and gamma. That is another reason. So, one term which we have studied is half life. Okay. Now, we have another term, that is activity is another term. You know what is activity? It is just the number of disintegrations per second. So, how many decays are happening per second, that is activity, right. So, that is nothing but mathematically we can write dN by dt. this is activity, dN by dt. This sometimes you represent with the letter R, the rate of decay. So, what is activity? Activity is the number of disintegrations happening per second. So, the specifically activity has got some special units. That is the place I told you we have to memorize, we have to remember those names of the renowned scientists Becquerel, Rutherford and Curie. Okay. So, the activity, the first unit is Becquerel. Okay. Becquerel symbol is BQ. So, 1 Becquerel is just 1 disintegration per second, otherwise just per second. This is 1 Becquerel. So, Becquerel is the SI unit of activity. We have another unit, that is Rutherford, symbol is RD. So, 1 Rutherford is nothing but 10 to the power 6 disintegrations per second. One more unit we have, that is Curie. The 3 names as the 3 units of activity. So, 1 Curie is nothing but 3.7 times 10 to the power 10 disintegrations per second. This is the biggest unit for activity. So, what I mentioned is activity. Activity is the number of disintegrations taking place per second. These are the 3 units and their conversion. So, if the question comes, what is the SI unit of activity? So, there is usually a 1 mark question like define activity and what is its SI unit. Activity is the number of disintegrations per second, its SI unit is Becquerel, or you can even write per second, there is second inverse. Right. Now, I will just show you a small very short video that indicates how the penetrating powers of the 3 radiations are. So, you can just make out clearly about in what way the penetrating powers of alpha, beta and gamma radiations differ each other. Just watch this video. So, you can see that alpha is coming, alpha, beta and gamma, all the 3 radiations. Just observe what is happening when alpha particle is going through a paper. So, a paper absorbs alpha radiations, alpha particles. How about beta? Through paper, beta is penetrated out. Okay. Whereas, you see gamma radiations can be absorbed only by lead block or container or concrete containers. Okay. Concrete or lead block, that only can absorb gamma radiations. All right. So, you have seen that alpha particle has the least penetrating power, beta particle has a higher penetrating power than that, and gamma radiations has the highest penetrating power. That is why we say gamma radiations are more dangerous. Okay. It will cause more harmful effects. There are many uses and harmful effects of these radioactive radiations. So, we will towards the end of the session I will show you some areas by which we can make use of the radiations, radioactive substances. Okay. Now, one more point, let me tell you, there is a specific law that is called law of radioactive decay, law of radioactive decay. Right. So, the law says dN by dt, that is the rate of decay is directly proportional to the number of radioactive atoms present. This is called law of radioactive decay. So, law of radioactive decay states that the rate of disintegration, that is number of disintegrations per second, is directly proportional to the number of atoms present originally. Right. So, we will put present now. Okay. We will put a negative sign. The negative sign indicates that the number of atoms decreases with time. So, we will further say dN by dt is equal to a constant which is represented by lambda. This lambda is what is called decay constant or disintegration constant. All right. Then dN by dt, then further like dN by n, we can rewrite like this, dN by n is equal to minus lambda dt. All right. So, on integrating this expression with the limits, like integrate both sides, integrating this over here from limits n0 to n, that is n0 is the original number of atoms or initial number of atoms, n is the number of atoms present now. So, if you integrate n0 to n over here in this side and 0 to t here this side, we will get an expression for the law of radioactive decay. On integrating this, the integration of 1 by x dx, you must be familiar with that, it is ln x or natural logarithm of x. So, by using that identity, we would be able to find out an expression. This expression on integrating this, we will get the expression as n equals n0 e raised to minus lambda t. See, this equation is what is called expression for law of radioactive decay, n equals n0 e raised to minus lambda t. So, what is the mathematical description about this equation? We see that this equation indicates the E means exponential, right, and power is negative. So, what you can make out from this? It shows that the number of radioactive atoms decreases exponentially. That is why we say it is decaying or disintegrating, okay, disintegrating exponentially with time. Okay, disintegrating exponentially with time is what is indicated by a graph. If you plot a graph between n and t, the graph you will draw like this. This is number of atoms originally present. Okay, so this will decrease like this. It is not touching x. Okay, so this is the graph showing the number of radioactive atoms with time, and this is what is indicated in the equation as well. So the equation shows that the number of radioactive atoms decreases exponentially with time, and this is what is indicated by the graph as well. Actually, there may be a question like you will be given this graph, and from the graph you are asked to find out what's the half-life. This is n0, so just find where n0 by 2 is, just half of it, right, and find out the time interval. Okay, so this interval of time you find, and this will give you the value of half-life. Okay, this is the value of half-life. It's clear. So you can find out the half-life, that is after this much time the number of radioactive atoms becomes half the initial number. Okay, this is what is called half-life, right. So we can make out, but there are some more aspects to understand from radioactivity. Let me tell you in a nutshell. You should know the terms like mean life, one. Decay constant I just mentioned, there is a definition for a decay constant, because it is a time for us to wind up for today's class. So I will just mention about what else is required related to this. One is the terms, related terms, mean life, decay constant, all right. Then alpha decay, beta decay, detailed description is required, and there is a small equation which is indicating the kinetic energy of alpha particle, all right. And after that we have uses of radioactivity. There are very good uses of radioactive isotopes. In fact, I was having a video. I will be able to, if the time permits, the next class I will show the video as well. Next day or next class we will come up with another topic, and meantime if you have anything to be explained, if you want me to explain something to you, surely you should get back to us and tell us this is something which you want to do through the live classroom. So keep watching the NTV's program, My Teacher, the live classroom or biggest classroom of the UAE. Keep watching, and next week we will come back with another interesting topic, and stay tuned with NTV. Thank you.